In the previous sections, we investigated what happens when two sound waves overlap. According to the principle of linear superposition, the resultant disturbance is formed from the sum of the individual waves. This principle reveals that overlapping sound waves exhibit interference effects, whereby the sound energy is redistributed within the region of the overlap. We will now use the principle of linear superposition to explore another interference effect known as diffraction. When a traveling wave encounters an obstacle or opening, it will bend around them. Take, for example, as the figure shows, a stereo speaker producing a sound wave inside a room with an open doorway that is propagating from left to right. As the wave fronts produced by the speaker reach the open doorway, they bend around its edges. If such bending did not occur, sound could be heard outside the room only at locations directly in front of the open doorway, as Part B of the drawing suggests, assuming that no sound is transmitted directly through the walls. The bending of a wave around an obstacle, or the edges of an opening, is called diffraction. All kinds of waves exhibit diffraction, and we will revisit this concept later on when we study electromagnetic waves. To see how the diffractive bending arises, let's look more closely at the sound wave passing through the open doorway. When the wave reaches the doorway, we know the air molecules located in the opening undergo vibrations, as that is the process by which the sound propagates. For purposes of illustration, we are showing only two of the air molecules. In fact, each of these molecules becomes a point source of sound, emitting sound waves in all directions, much like a stone dropped in a pond creates circular water waves in 2 dimensions. The sound waves generated by all the molecules in the doorway must be added together to obtain the total sound wave at any location outside the room in accord with the principle of linear superposition. The net effect is a bending, or diffraction of the sound wave around the edges of the opening. Further insight into the origin of diffraction can be obtained with the aid of Huygens' principle, which we will explore in section 27.5. Because of linear superposition and the consequence of constructive and destructive interference, it is found that there are places where the intensity is a maximum and places where it is zero. Analysis shows that at a great distance from the doorway, the intensity is a maximum directly opposite the center of the opening. As the distance to either side of the center increases, the intensity decreases, reaches zero, then rises again to a maximum, falls again to zero, rises back to a maximum, and so on. Only the maximum at the center is a strong one. The other maxima are weak and become progressively weaker at greater distances from the center. In the figure below, the angle theta defines the location of the first minimum intensity point on either side of the center. The following equation gives the relationship between theta, the wavelength of the sound lambda, and the width of the doorway d. This assumes that the doorway can be treated like a slit, whose height is very large compared to its width. Waves can also diffract through openings that are not rectangular in shape. Circular openings are very important, especially in applications involving round speakers, for example. In this case, the angle theta that locates the first minimum is given by the following. It is important to remember that the extent of the diffraction described by the above relationships depends on the ratio of the wavelength to the size of the opening. The amount of diffractive bending we see goes as lambda over d. In other words, we see more diffraction for longer wavelengths and smaller openings. Since high-frequency sound has a relatively small wavelength, it tends to have a narrow dispersion. On the other hand, for larger values of the ratio lambda over d, the angle theta is larger. The waves spread out over a larger region and are said to have a wide dispersion. Low-frequency sound, with its relatively large wavelength, typically has a wide dispersion. As a final note, we have seen that diffraction is an interference effect, one in which some of the wave's energy is directed into regions that would otherwise not be accessible. Energy, of course, must be conserved during this process because it is only redistributed during the diffraction. No energy is created or destroyed.